right, good morning. Hope everybody's doing well. Hope you had a good weekend. For those keeping score, DHL has not delivered my package. They have informed the shipper that because of a blizzard in Portland, it's very difficult to deliver packages right now. So, apologies for the blizzard that I guess is happening. Yay, DHL. All right. Any questions? We're going to talk about ODP 215, and then we're going to start talking about sorting. Yeah, an event majeur is what their website actually says related to weather. And they use the word blizzard when they talk to the shipper. Somehow UPS is right outside. I guess they managed to get through the blizzard. All right, let's hop into the ODP. So 215. So this is yeah, UPS rocks definitely. I thought DHL rocked too. I mean, I used them for a few of these printed circuit board shipments, and now they're just kind of, I don't know. You know, my other set of boards showed up last Thursday morning, and they still haven't made it across the bridge to me. So I don't know what's going on with that. All right, ODP 215. This is related to our deletion from a binary search tree. And the first part of deleting is getting down to where you're deleting the root. So that's the recursive part. And that's, you know, if your number's smaller than the root, then delete from the left subtree. If it's bigger than the root, delete from the right subtree. Otherwise, we're going to delete the root. And to delete the root, the first thing you do there is find the largest node in the left subtree. So that's what this ODP is asking you to do. So you're writing a function named largest, which accepts the root of a tree, and then tries to find the largest data value in the left subtree. So, you know, to actually do the deletion algorithm, you would need to go down. You'd actually need to find the root node. You'd need to know who its parent is, and eventually you're going to move that root node up to be the root of the tree. But for this ODP, all you're doing is looking for that largest node. So you're just traversing the tree, starting with the root of the left subtree, moving as far right as possible, and then just returning the integer value, because our node still just looks like, you know, an integer and 2 pointers. So the algorithm discussed in class, which we'll rediscuss right now, right? Start at the root of the left subtree, and you're guaranteed the left subtree exists in this case. I won't give you a tree with nothing on the left. So move down to the root of the left subtree, and then just keep moving as far right as possible. When you can't move any further right, the data value of that rightmost node, that's what your function should return. Let's see, they're a week behind in terms of weather. Yeah, that could be. I'm really curious if they'll deliver my package that's supposed to be delivered today. All right, any questions on this this ODP? And the guts of this code is really no different from what you were doing with linked lists when you were trying to move to the end of a list. If you wanted to find the last node in a list, you would just keep moving down until the next field is null. Well, here you're going to keep moving to the right until the right field says it's null, and then just return the data value of that node. I don't think I have any more ODPs lined up for this week, so this may be it for the week. But you got PA4, so that'll keep you busy. All right, well, let's talk about sorting. Sorting is one of these classic problems in computer science, where you have a collection of data and we'll usually talk about numbers just because it's a simple case to work with. But it could be anything. It could be numbers, could be words or sentences. It could be binary data. But it's something that you want to put in some kind of order according to some kind of comparison function. So for numbers, we just say greater than, less than. For strings, we use string compare, which is what you're using in PA4, because you're sorting based on license plates. So there's some kind of comparison operation. And, typically you start some set of data in no particular order, and you want to rearrange it, say, from smallest to largest. And I'll pretty much stick with smallest to largest in these lectures, but, it could be sorted the other way, exactly the same algorithms. And so how do you do this? Well, there's a number of ways you can sort data. And some of these ways work really well for small amounts of data, but they start to get very slow as the size of your data increases. And some of these continue to work well as your data gets really, really large, but they have a lot of overhead. They might actually take a lot of time, and if you're sorting a small amount of data, they might take more time than something like a simple bubble sort, right? Some of these work really well if your data is almost sorted to begin with, if it's just slightly out of order. Some of these work terribly if your data is almost sorted to begin with. One of the fastest sorts that we'll talk about is called a quick sort, right? Marketing. And quick sort is really, really good unless your data is almost sorted to begin with. And then it's worse than bubble sort in terms of performance and complexity. So there's lots of different sorts. And in practice, we don't usually write our own sorts. We usually use a sort function or a sort utility. And search engines will do their own algorithms, but search engines don't usually just sort data and then do a high-low, right? The real sort of secret sauce of Google and all these others is using heuristics and some kind of associative network or something to go from a search term to a corpus of data, a set of web pages that seems relevant. And that's a whole nother level of algorithm that we won't get into here, but you can get into in some university courses. And for the most part, if we need to sort data in code, we're going to call a sort function. It's probably going to be a quick sort or something like that. And we don't even necessarily know what the sort algorithm is. We just know it's a fast one. But for this course, we want to actually go through the nuts and bolts of different sort algorithms. One, because it gives us some idea of sorting, right, which is kind of a fundamental problem in computer science. Two, it's a interesting collection of algorithms. Three, some of these algorithms are recursive, and they provide a really good example, further example of how recursive algorithms kind of come up and can simplify complex tasks. So what's the sort of most fundamental sort that you may have encountered so far? Give me the name of a sort. I'm waiting for DHL to call, so my ringer is on. So I know you learn how to sort things in 121, and we did some sorting in 224. So someone name a sort for me. Bubble sort, there we go. That's sort of the first sort that we generally run into. So let me grab a deck of cards here. All right. So let me shuffle these up. All right. So here's a set of cards, right? And we're just going to use these for sorting. So ace is low, that's a 1, and then jack is 11, queen is 12, king is 13. So yeah, merge sort is another good sort we're going to talk about. That's one of those recursive sorts. So let's start with bubble, right? What's the idea of bubble sort? Basically, you make a series of passes through your data, and each time you run through your data from beginning to end, you take the largest or the heaviest element and you move it to the bottom, right? So how do we do this? We compare each number to the number right below it. So we'll look at a 6 and a 5. And so we're going to sort these with smallest number on top, largest on bottom. Okay, we compare the 6 to the 5. The 6 is bigger. It should be below the 5, right? And this is bubble, as in, you know, things falling to the bottom of the ocean. So here's a 6, 5. Here's an 11, 2, 12, 9, 10, 7, 8, 3, 1, 4, 13. All right, so there's our data we're sorting. So the idea is we're going to make a pass through this data and hope that at the end of this pass, the largest number is at the bottom. It happens to be at the bottom already, but that's okay. The way we do this is by taking the first number, comparing it to the second. And since we want larger numbers to be at the bottom, these are in the wrong order relative to each other. So we're going to swap them. And then we're going to compare that 6 that we just swapped to the 11. And 11's bigger, so 11 should stay on the bottom. We'll compare 11 to 2. Those are out of order, so we'll swap 11 and 2. And then 11 and 12, 12 is bigger, so that should stay on the bottom. 12 and 9 is out of order, so we'll swap those. 12 and 10 is out of order, so we swap those. 12 and 7 out of order, and in fact 12 is going to swap with every one of these cards. 12 is definitely bigger than 1. 12 is bigger than 4. And when we get to the bottom, 12 is smaller than 13, so it's not going to swap. Okay, what we know at this point is that the largest number is sitting down here at the bottom, our array. This is an array. And if you want to convince yourself that this works, right, whatever the largest number is, let's call it L, right, it's going to be bigger than every number. So wherever it is in this array, it's always going to swap with any number below it, right, until it gets down to the bottom of the array. If the largest number is sitting right here, well, since it's the largest, it's bigger than this number, so it's going to swap. And at the end of this one pass, your largest number is going to be in the bottom position. All right, what if we make a second pass? Well, 5, 6, 6 and 2 should swap. 6 and 11 is fine. 11 and 9 should swap. 11 and 10 should swap. 11 and 7. 11 and 8. 11 and 3. 11 and 1. 11 and 4. 11 is smaller than 12, so that's okay. 12 is smaller than 13, that's okay. And guess what? We've got 3 cards in the right spot now. Let me do one more pass. 5 and 2, those are in the wrong order, so we'll swap them. 5 and 6, that's fine. 6 and 9, that's fine. 9 and 10 is fine. 10 and 7, wrong order. 10 and 8, wrong order. 10 and 3, wrong order. 10 and 1, wrong order. 10 and 4, wrong order. 10 and 11, fine. 11, 12, 12, 13, fine. So the effect is if you picture your numbers as being, you know, sort of large rocks, they're sinking down to the bottom of this pile and falling into the correct spot. And each time we go through, one more number will sink down into its correct spot. And so when we code this, it usually looks something like this. So this is pseudocode, details aside. We have an inside loop. We call this one pass through the data. And during this pass where we go through, you know, each piece of data in our array, we compare that piece of data with the piece of data after it. And if they're in the wrong order, if this piece of data is bigger than that one, we swap them. And at the end of this loop, one piece of data has moved into the correct spot. And since we have n pieces of data, if we just repeat this inner loop n times, that will sort the entire array. So this is assuming that we're testing and comparing and swapping, right, to sort a set of n pieces of data, so an array of length n. So the first question is, how many times potentially will this inside operation of comparing and possibly swapping, how many times will that be executed if our array has n elements in it? It's not exactly n factorial. It's actually not as bad as n factorial. But it's worse than n minus 1. N squared. Okay, I like that one. Right? A rough approximation, this loop is going to execute n times, right? Test goes from 1 to n. And this outer loop is also going to execute n times. And in each of these n passes, this inside loop's going to execute n times. So that's roughly n times n, which is n squared times that this thing's going to be executed. Yeah, very nice. All right, so we're going to talk a lot about order of complexity, and this is an example of what we would call an order n squared algorithm. All right, what's the intuition of order n squared? Alright, so we have a pass going from 1 to n. Inside each pass we have test going from 1 to n. Alright, so if n is equal to 3, this inner loop's going to happen 3 times for each pass, and we're going to have a total of 3 passes. That's going to be 9 times we're doing this comparison and possible swapping. If n is 6, this inner loop, one pass is going to take 6 comparisons. And we're going to do a total of 6 passes. That's going to be a total of 36. tests and possible swaps. Right, so exactly, we double the amount of data, we quadruple the amount of time, the number of operations we have to perform. If we increase the amount of data by 10, we would increase the amount of time by 100. So the time complexity is increasing by the square of the problem space complexity. So that's the quadratic nature of an order n squared problem. And if we're sorting, 10 numbers, don't care, Taking 10 operations, taking 100 operations, taking 1,000 operations, it's all trivial, right? But if we had 1,000,000 pieces of data to sort and we tried to use a bubble sort, that's going to be on the order of 1,000,000,000,000 times that this inner code is going to be executed. And when you start talking trillions, that's a lot of time, right? If you're running at a gigahertz and you could actually do one of these every clock cycle, which you can't, right? You could do 1,000,000,000 of them in a second. To do 1,000,000,000,000 of them would take you 1,000 seconds. So now you're talking about 20 minutes, right? And that's assuming that your whole loop takes a single clock cycle, which it doesn't. So this is a really expensive sort when n starts to get large. But it's a pretty quick sort to code up, right? I mean, you can take this pseudocode and you can, more or less write this directly. The trickiest part of a bubble sort is really just this swap. And once you've done C code to swap two numbers a few times, it doesn't take too much thought. Now, you can make improvements on a bubble sort. For example, when we were sorting these cards, you may have noticed that, once the king was at the bottom, whatever card came down to the bottom at this point was always going to be smaller than the king. So we didn't really need to compare this last card with the king again. And once we had two cards in their final position, whatever card came down to the bottom of this pile didn't need to be compared to the queen, and the queen didn't need to be compared to the king. And once we have a 10 that comes down in the right spot, we don't need to compare it to any of these. And so this outer loop can actually be made more efficient. We don't need this inner loop, right? We don't need to compare every number with every other number. We can actually stop. We can go up to, n minus something. And so if we have, let's say, 10 pieces of data, well, the first time through, we actually only have to do 9 comparisons, right? It's not actually n, it's n minus 1, so we have to do 9 comparisons. And that'll move the largest number into the bottom. The next pass, we don't have to compare anything to that largest number, so we only have to do 8 comparisons. And the next pass, we only have to do 7 and 6 and so on. And so this is going to come out to approximately n squared over 2. But order n squared over 2 is still order n squared. Right? If we double the amount of data, this thing, even though it's smaller than n squared, will still double. Will still quadruple, right? So when we compute these orders of a complexity, we tend to just throw away constants because they don't really change the, in this case, quadratic nature of the time growth. So this is going to be order n squared. The other embellishment we can make is what happens if our data happens to be sorted. What happens if we've gone through, 3 passes and now, by some magic of the universe, our data is perfectly sorted. we don't really need to make any more passes. Subsequent passes will not change the order of the data. And we can capitalize on that. So let me show you this. All right. So here's your data, and maybe we've only done 4 passes, and our data happens to be sorted. So what happens on our next pass? We compare 1 to 2, that's smaller. 2 to 3, that's smaller. 3 to 4, smaller. We do all of these comparisons, and we never end up swapping anything. And so we can set a flag in here, and we can say, hey, anytime that you swap data, set a flag. And then this outer pass, instead of counting and doing this n times, we can do this until we've done our inner loop and not set a flag. And once that happens, we know our data is sorted and we can exit at that point. And sometimes that'll save us time. And on average, it's going to save us half the amount of time. So our n squared will again get cut down by 2, but it's still order n squared. But we can make it, work well if the data is close to sorted to begin with. All right, so 2 other sorts. So first one is a selection sort. And the other one's going to be insertion sort. And they're very similar to each other, and it's easy to get them confused with one another. So here's how I think of insertion and selection. The question is, when do you do the work involved in sorting your data? So both of these sorts will start with an array of data, and we'll move the data from here to an output array. And the goal is your output array should be sorted. So you got to do some work somewhere. But there's 2 places you can do the work. You can do it when you remove from the input pile, or you can do the work when you insert into the output pile. Okay? If you do the work when you're selecting from the input, that's a selection sort. If you do the work when you insert in the output, that's an insertion sort. So let's do selection first. All right, how does this work? Basically, go through your array and pick the smallest number. Well, let's pick the largest number. Okay, going to go through our array. We're going to find the largest number. How do you do that? Well, start off and let's just say 4 is our largest number. So initialize your loop with the largest equal to the first element in your array. And then if the next element is bigger than largest, set largest equal to that. Well, 1 is not bigger than 4. 7 is bigger than 4, so 7 is going to be my biggest element. 2 is not bigger, so it's still 7. 11 is bigger, so 11 is my biggest element. 5 is not bigger. 10 is not bigger. 6 is not bigger. Remember, 11 is my biggest element. 3 is not bigger. There's a 13. That's bigger than 11, so that's my biggest element. There's a 12. There's an 8. There's a 9. So what's my biggest number in my selection sort? The biggest number I found was 13. Okay, I select that and I put it in my output pile. That's one pass of selection sort. I'm just going to do that 13 times. So exactly the same thing. I'm going to go through my input pile. I'm going to select the biggest element. Start with 4. 1 is smaller. 7 is biggest. 11 is bigger, so that's my biggest. Smaller, smaller, smaller. 12 is bigger than 11. That's my biggest. 8 and 9 are smaller. 12 is my biggest element. I'm going to take that, add it to my output pile. Right? Very straightforward. No doubt that this is going to leave me, with a fully sorted output pile. I'll do one more pass. 4 is my biggest element to begin with. That's smaller. That's bigger, so 7 is my biggest. Smaller. 11 is bigger than 7, so that's my biggest. Smaller, 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 smaller. 11's my biggest number. I'm going to take that, add it to my output pile. So what does this look like in pseudocode? Let's do one pass. So let's do largest equals our first element. So we'll go through and look at each element from 1 to n, and if that element is bigger than our largest, then what do we want to do? We want to set largest equal to that number. And we want to remember where that is, right? So when I was doing this with cards, I just kind of kept my thumb on the biggest one so that when I was done, I could pull it out, right? But we need to keep the index. So largest equals data 0, and the index of the largest is 0. If the ith element is bigger than our largest, set the largest to, that element, and set our index equal to I. And so do that whole loop, and when we're done, this is our largest number, and this is where it was found in our array. So how do we pull it out of the array? Well, you got a few possibilities. If you're using two arrays, right, we just copy it to an output array, but we need to remove it from this input array so that we don't count it as the largest next time through. So how do you delete from an array efficiently? Well, you move it to the bottom of the array, so swap it with the last element in the array and change the array's length to be one smaller so that, that number doesn't get counted again. But there's fancier ways you can do this. You could actually sort this with a single array and just keep moving, your largest element down to the bottom end of the array and so on. But I'm not interested in those details right now, right? I'm looking for first order complexity. So this pass is going to take basically, n steps. And for each pass, we select one thing to go into our output pile, which means we need a total of n passes. And that's going to happen n times. And so this is still going to be an order n squared. So it is order n for a single pass, you're right. But then we have to do n passes. So order of complexity, selection sort, no better than a bubble sort. All right, questions on selection. Hold on, I got a weird message here. Interesting. Cool. Alright, my replacement boards are coming today. I ordered these like last week. And they got made in 2 days, and they made it through customs in China in less than a day. And made it to Portland this morning. Yeah, exciting stuff. All right, so that's selection sort. And like I say, the way I remember this is, sort when selecting from the input array. And so what's going to happen if our data is sorted or close to sorted to begin with? If our initial input array is sorted, is that going to change the amount of work we have to do? Probably not. All right, because even though our data might be starting with well, let's go largest to smallest. Even if our largest number is on the bottom to begin with, right? Or if our largest was on the top to begin with, we still need to look through the entire input array to know that that's the largest or the smallest number. And then, adding it to the output array is a quick operation. All the work is happening in the selection, and having your data sorted or not sorted doesn't make any difference, right? So we don't really get a benefit, but we also don't get a penalty from the data being sorted to begin with. All right, so the flip side of this is the insertion sort. So insertion, we are doing the work when we add things to the output pile. So let's go smallest to largest again. So what do we do for insertion sort? We always take the first element in the input array and we put it into the output array so that the output array remains sorted. Okay, so our output pile is empty to begin with, so the 2 simply goes on top. All right, take the next card from the input off the top. That's a 3. And we put it into the right spot in the output array so that the output array is sorted. Well, compare a 3 to 2. 3 is bigger, so it's got to go below. And that's the bottom of the pile. So there's our output array now. Okay, take the next card off the top. No work in selecting the input card that you're going to deal with. Just take the next card in the array. That's a 9. Okay, 9 is bigger than 2, so it should go below. 9 is bigger than 3, so it should go below. And there's nothing there, so it goes on the bottom of the pile. Take a 4. 4 is bigger than 2, so it goes after that. 4 is bigger than 3, so it goes after that. 4 is less than 9, so it goes right before that. All right, you see the difference from a selection? Selection, we were choosing a card over here and then just popping it on top of the pile. Insertion, we're taking a card from the top of the pile, but we're choosing where to insert it into the output. So there's a 5, it's bigger than a 2, bigger than a 3, bigger than a 4, not bigger than a 9, so it goes right there. There's a 10, it's bigger than a 2, bigger than 3, bigger than 4, bigger than 5, bigger than 9, there's nothing else, so it goes on the bottom. There's a 7, it's bigger than a 2, bigger than a 3, bigger than 4, bigger than 5, less than 9, so it goes right there. So back when I graded, physical papers, I think I tended to use an insertion sort, right, to alphabetize names. I would take the next, exam off the pile, and I would flip through my growing stack of sorted exams, and I would put it in at the right spot, right? That seemed to work for me. But I wasn't thinking insertion sort. That's just what I did and tried to figure out what my algorithm was. All right. So that's basic setup. So what do we do? So one pass. Pick the top card, and then go through each element in your output array. So this is not n, this is however many things you have in your output pile right now. So for each card in that, if your card is less than that ith card, then insert it right before position I. Use insertion sorting when cleaning your room. That's interesting. I'm wondering what you sort. So what's the order of complexity of this? Well, to do one pass, oh, that makes sense. To do one pass, right, we need to basically take your next piece of data and compare it to potentially every piece of data in your output array. Now, you'll probably end up stopping before you get to the end. You'll find something bigger than that and say, okay, it's got to go in here. And, you know, you may luck out. I may, you know, find that the first thing that I compare it to is larger, and so my card goes on top. Or you may be very unlucky and have to compare every card in your pile until you run out of cards and say this was bigger than everything, and it goes on the bottom. But average, you know, it's going to be n over 2 comparisons until you find the right spot to insert a card. So, you know, average would be order n over 2, but that's the same thing as order n for one pass, and then you have n passes because you have n cards coming in. So this is again order n squared. And the mechanics take some work. So if I'm going through my data and I find that my 6 should go right here before the 7, right? If I have a linked list, I know I can do that insertion easily, but if this is an array, right, how would I insert the 6 between the 7 and the 5? Well, I would have to move everything down one spot to make room in the array for this new element. But I can do that as I'm moving through my output array, right? I know that if my number I'm inserting is bigger than 1, then I'm going to need some space somewhere, so I can go ahead and move this down one spot. And I can do the same with the 2 and the same with the 3 and so on until I get to the spot where I want to do the insertion, and then I've made space for it. So if you work out the details of that code, it still ends up being roughly order n squared. And how does insertion sort behave if our data is sorted to begin with? Is insertion sort affected by having the data sorted to begin with? So suppose my data was sorted in reverse order to start. and I'm doing my insertion sort. Okay, I'm going to take the first card, that's a king, and I'm going to say let's put that in the right spot in the output pile. Output pile is empty, so it goes right there. One operation. Take the top card, that's a queen. Let's find the right spot in the output pile. Well, I'll compare it to the first card. It's smaller than that, so it goes on top. That's one operation. Take the next card, that's a jack. Let's compare it to the output pile. Compare it to the first card, it's smaller, so it goes right there. Other than the mechanics of perhaps making space in my output array, right, I'm not doing a lot of comparisons. I'm pulling the top card off. I compare it to the first card in my output and see right away this should go before that card. So this is actually like really efficient. This is going to end up being order n to do the entire sort, because my inner pass, which is looking for the right place to insert, is really just going to be order 1. Now again, if this is an array, you know, that I initialize to 13, and then I want to, you know, put the 12 before that, then I would have to move that 13 down and put the 12 here. And the next time I would have to move the 13 and the 12 down and put the 11 there. That's going to kill my performance. But if I suspect my data might be sorted to begin with, I can take advantage of that, right? Or I could store my output data in a linked list, because I don't do any kind of, you know, high-low search on this. And I could actually get an order n insertion sort. Nominally, these are all kind of equivalent though. Bubble, insert, select. And different details for coding them. All right, what about data movement? The other thing we want to think about in terms of performance of algorithms is how much data we're moving around and how far it's moving. Now, why do we care how far data moves? Why do we care if we're moving something from here to the bottom of the deck or moving it just one spot below it? What's the difference? This is an Engineering 270 question. I'm not going to do my Matthew Broderick impersonation. Remember cache memory? So data caching is a serious aspect of computing performance, right? Data caching is based on the notion of locality, and there's spatial locality and temporal locality. And the concept is that, you know, spatial locality, if you access something at this point in memory, there's a good chance that subsequent accesses will be near to that in memory. Typically, we don't access data at totally different dispersed spots in memory. We access memory in little localized regions, and that's what caching takes advantage of. If you do a bubble sort, you're always comparing a number to the number after it. That's spatially local. And if you're swapping a number with a number after it. That's spatially local. And as you move through the array, that point of locality changes, but you still maintain a high degree of spatial locality. Okay, think about that in terms of insertion and selection sort. See if you have that same kind of local reference characteristic, or if you tend to move around a lot. All right, we are out of time. So we will look at some better sort algorithms tomorrow, some ones that are n log n. This will be quick sort and merge sort that we'll start with, and then we'll go on to radix sort and some other comments. All right, so we'll pick that up tomorrow. Thanks.